Morning. In this session, I would like to demonstrate a problem involving a flash calculation. Probably in your thermodynamics course, you would have solved a flash problem, typically TP flash, and even in the case when you are trying to use Raoult's law describing the vapor-liquid equilibrium, this problem involves an iterative solution, even when the temperature and pressure at which the flash column is operating. Even if you know this, the solution is going to be iterative in nature. Now, the problem will be much more difficult in case if you are given with pressure and vapor fraction, temperature and vapor fraction, pressure and heat duty, temperature and heat duty. Probably some of these calculations are going to be tedious. In case of other problems, you might have seen how to solve a flash problem only when temperature and pressure are given to you. I don't go into the details, but you can verify the basic equations that are necessary to solve a flash problem. Now in this case, we are dealing with a mixture, a binary mixture of benzene and toluene. The feed is at 1 bar and 25 degrees centigrade. We are going to simulate a flash column given some of these conditions. Suppose if you are the pressure and the vapor fraction resulting from the flash column, you are required to simulate the flash and calculate the temperature at which the flash column must operate and also the associated heat duty that need to be supplied. Similarly, when temperature and pressure are given, you are required to identify the flash model results and see whether you are able to get a fraction of 0.5 or not. So like this, right? So we are going to make use of two components, benzene and toluene, and we will try to solve this simulation using all these 5 different types of inputs. In fact, all of them should be able to give you the same type of result. So let us go back to Aspen and try to simulate this problem using a flash model. So as you can see, we are using only two components, benzene and toluene. Go to the next input screen. So choose a property model. Let me consider something like Java Cedar. Go to next input screen. Go to simulation environment. Now you can see the flash columns are available under the tab separators. You can see the difference between flash 2, which is 2 outlet flash models VLE, vapor liquid equilibrium. And if you want to model vapor liquid equilibrium, you need to go for flash 3. So in this case, we are dealing with only vapor liquid equilibrium. So let me select this flash 2 model. And connect the input and outputs. This is the feed stream, and this is your vapor stream, and the bottom liquid stream. Right? So let us go to the next input screen. So we are given the temperature and pressure at which the feed is coming in, 1 bar and 25 degrees centigrade. And you can assume some flow rate, 100 kilomoles per hour, and we know the mole fractions. It is mentioned that it is a equimolar binary mixture. So the composition is 0.5 and 0.5 mole fractions. So we were able to define stream 1. Let us see what information is required when we go into the flash column. Now you can specify any of these possibilities: temperature, pressure, pressure duty, pressure vapor fraction. Similarly, temperature, pressure, temperature duty, temperature vapor fraction. So let us take the first option. Pressure is given as 1 bar and we wanted to vaporize 50% of the feed and 50% should be in the liquid. And we don't know at what temperature the system or the flash column should operate. So pressure is 1 bar and the vapor fraction is given as 0.5. Now you can just see whether with this kind of specifications, will you be able to calculate the temperature at which you should be operating the flash column in order to generate 50% vapor and 50% liquid at this pressure. So you can see the required input is complete. We should be able to run the problem. Yeah, we got to our results. Let us look at stream summary. Now you can see the pressure is given as 1 bar and the inlet feed is coming at 25. But these are the two outputs from the flash column. S2 is the vapor product, S3 is the liquid product. You can see that from molar vapor fraction. So only when you are able to operate the flash column at a temperature of 95.4, you will be able to get the mole flows. You can see 100 is the input flow. When you want to vaporize 50%, 50 moles per hour of vapor product is obtained and 50 moles per hour of liquid product is obtained. And what about the compositions? So this was the inlet composition, but the compositions of the outlets are something like this. About 40% toluene and 60% benzene, right? Now from this, you can also look at, we know that now the temperature. Let me see what is the second. So already we know the pressure is 1 bar. Now the temperature has been calculated from the first part, right? Which is 95.3997. Let me copy this value and go back and adjust the input for the flash column. Now instead of specifying vapor fraction and pressure, I am going to specify the temperature that is just now calculated and try to run this problem. So what should we get? We should be once again able to get the same pressure. The flash column must be able to, the flash column should be able to give you 50% liquid and 50% water, 50% liquid. One more thing is, let me go back and check up this result as well. So in order to do this, the heat duty has been this much, 1,77,259, or let me put it in maybe kilocalories. So 63,8133, right? So you can compare this value maybe later. Okay. So let me run this problem with the change in specifications. Instead of vapor fraction and pressure, now we have specified temperature and pressure. So once again, you can look at the stream summary. So once again, you could see that the same vapor fraction of 50 is obtained. So 50 kilomoles per hour of vapor is obtained and 50 kilomoles per hour of liquid is obtained. And you can also compare that the compositions of the vapor and liquid were similar to the previous calculations. In the same way, you can also look at the heat duty. The heat duty is also similar to whatever we have calculated earlier. So in other words, we are trying to solve the same flash problem with the different types of inputs. Now, in the first case, we have given pressure and vapor fraction. In the second case, we have given temperature and pressure. Now, in the third case, we wanted to specify temperature and vapor fraction. Right? I think did you observe the result summary? Now you can see these two are given. Now we were able to calculate the vapor fraction and the composition along with heat duty. Once again, let us go back and change. Instead of temperature and pressure, now I would like to consider temperature and vapor fraction. Remember, this temperature was calculated giving a pressure of 1 bar and 0.5. Now we used the temperature and pressure and verified that we were able to generate 50% vapor. Now with 50% vapor and at this temperature, we should be able to run the simulator. We should be able to operate the flash column only at 1 bar in order to obtain 50% liquid and 50% vapor. So let me once again run this problem. Now let us look at the stream summary. Now you can see, though we did not specify the pressure has been calculated as 1 bar. And once again, we were able to obtain 50% of liquid and 50% of vapor, again with the same composition. Now similarly, you can go back. Of course, you can also check up the heat duty now. It would also result in the same heat duty that we observed in the earlier parts. Now let's look at pressure and heat duty. Right? let me copy this heat duty and go back. Now we are supposed to give pressure, which is already known. Instead of temperature, now I am going to give the duty. Let's check up whether the duty was similar. Units, calories per second. So once again, with this pressure and heat duty, we should once again be able to get back to the same temperature and 50% liquid and 50% vapor. So once again, you can see the temperature has been calculated as same as the previous one, 95.3997, and we were able to get 50% liquid, 50% vapor with the same compositions. In the same way, you can also do the last one, temperature and heat duty. So instead of pressure, let me select temperature. Now only these two inputs are given, temperature and heat duty. We should be able to calculate the pressure as 1 bar, and in order to get vapor. Once again, you can run this problem. So you will be able to observe that we will be able to calculate 1 bar and 50% liquid and 50% vapor with the same composition. So in this problem, we were able to simulate a flash column with 5 different types of possible inputs: pressure and vapor fraction, temperature and pressure, temperature and vapor fraction, pressure and heat duty, and temperature and heat duty. Probably, if you are trying to solve a flash problem analytically, we know how to handle this particular calculation. Even this calculation is going to be iterative in nature. You can just verify from your thermodynamics, whereas other calculations are going to be much more tedious than when you are given with temperature and pressure. So anyway, you can check up those analytical solutions. Already have been introduced to flash column. So with this, I would like to stop